Okay, so welcome back everyone for this first afternoon session. And yeah, so far everything went very well. Thanks all for attending. And our next speaker will be Ján Pulmann from the University of Geneva. And he will talk about perturbative Chern-Simons theory with chiral boundary conditions. And yeah, so the stage is yours.
Thank you very much. So I'm very thankful for the organizers for giving me such a generous time slot. I don't know what they were thinking. So this is a report on a joint work with Donald and Pavel Severa. You can find it on arXiv, for example. And I will start again with talking about Chern-Simons as the two previous speakers. So hopefully you will not be too bored. And I thought that I would just list like people who also talk about Chern-Simons, and then I realized I would need to list most of the speakers. So apparently it's a common theme in this conference. Okay, so let me recall that for Chern-Simons, one needs an oriented free manifold and an Lie algebra with an invariant metric. And then one can write the following function on the space of all first connections on a let's say trivial principal bundle over M. So S. But actually, I want to go direct to the BV formalism. So for me, A will be now just a form on the module on the space M on the manifold with values in the Lie algebra G. Okay, and this function is defined as follows. So it's integral over M of 1/2. So you take this form and you pair it with D of itself, plus you take the form and pair it with the commutator with itself. Okay, so this already includes this BV formalism thing, in the sense that this A, it has 4 components, right? So A has component A0. This is just a G-valued function, a 1 form, 2 form, and a 3 form. And if you are from physics, so this would be the ghost. This is the field, the connection, and these two are the anti-fields. And so the goal of studying Chern-Simons theory in quantum mechanically is to define this following nonsensical integral. So we want to integrate over all such things, such A's, and we take exponential of IS over H bar, and I will also put some other function of this connection here as well. This, I don't know, this could be, I will do an example where this F will be a holonomy around a loop for this concrete A. And so this is the issue that there I write dA, but there's no mathematical sense one can give to this thing. So and this is called the expectation value of F. Yeah, you also need to be precise. You need to also divide by just integral of S. Just integral of EIS. Okay, so now I will give you probably most of you know this maybe better than me, but I will give you a crash course, the shortest crash course on Feynman diagrams ever. So in finite dimensions, when you want to calculate the following integral. So those AI, these are variables, and you pair them with some symmetric matrix, and then we multiply some f. Okay, so this is your integrand, and you integrate over just the finite dimensional space of A. A's, okay, like this. This is inverse. So maybe write it like this. Okay. DAI, DAJ, acting on F, and then you set A to 0. Okay. And now if you think about this, what kind of formula, what kind of terms this expression can allow? So you need to look at if your F is just a monomial, then you need to differentiate. You need to kill all those A's by those partial derivatives, because otherwise the result is 0 by setting A to 0. So you just get all possible ways to connect those A's in F. And so this is the reason why we get Feynman diagrams, because you look at all possible ways to connect some flags. So let me write it. So let me be more precise in this context of Chern-Simons theory. So you sum over all these Feynman diagrams, and so how do they look like? So here, this was maybe not a good notation. So let me write F tilde and F tilde, because in this case, this F for Chern-Simons, the F tilde would be actually exponential of the cubic term of the action times F. Okay. So in this exponential, you can take as many cubic terms like this as possible. So the Feynman diagrams, they will have trivalent vertices, because this is a cubic term in A. And then they will have external vertices given by F. By F. Okay. And so when you draw such a diagram, what you need to do, you need to assign some kind of number to it. And so what kind of number is it? So what you do for each trivalent vertex, you write just the structure constants of the Lie, or let's say just the Lie bracket, and you see it as a, right? So this is an element of G dual tensor G dual tensor G, but your Lie algebra is equivariantly, it's invariantly isomorphic to its dual. So this is just element of, let's say, G dual tensor 3, and then to an edge, you associate something which is called a propagator. So this will be a 2 form with values in G cross G. Okay. So let's just look at what happens with the Lie algebra factors. So, right. So for any, I don't know. Let me write an example. So from the propagators, you get an element in G tensor G power number of edges, and then from the vertices you get G dual times power number of 3 times number of vertices, and the Feynman rules that tell you that now you should just contract these things together in such a way, in the same way as the diagram tells you that they are adjacent, right? So there is alpha, beta, gamma, and there is E and F. You have to pair this element beta and this E. And so these are so-called chord diagrams. This is how you get them from Chern-Simons. This is how you get actually not invariants from Chern-Simons. Okay. But what is actually more interesting is the propagator, and sorry, is the two-form part of the propagator. So let me talk a little bit about that. So if you look up, what we used here was an inverse of the quadratic part of the action. So here the propagator should be something like the Derham differential inverse. So first, let's just assume that the Derham differential is invertible. Otherwise, I think this is what Konstantin talked about. Then you don't get a number, but you get some kind of element, a function on the cohomology. Okay. Okay, and there, like historically, there were two, for Chern-Simons, there were two solutions for this. One of them was by Axelrod and Singer, who chose a matrix on the manifold M, and then basically you choose D as the codifferential induced by the Hodge star. Actually, you need to, yeah, let me write it like this. But then the Kontsevich came and he just wrote down a propagator. So this is also a possibility apparently. So let me write it down. No, first I will just tell you what kind of object is it finally. So this propagator, it is a form. It's a two form, and on the so-called configuration space of points in M, and I was talking about the inverse, now I'm talking about the two form, and the connection between these two, that is P, this two form is an integral kernel of this operator D inverse. Okay, and let me write those two components like in the Lie algebra as this. So being an integral kernel, it means that if we have a one form, then this should be computed as convolution with this kernel. So X2. I'm sorry, I ran out of paper. Okay, and it should also of course satisfy some Knight's properties such that so that the quantization makes sense. Okay. for example, that this operator D inverse is actually inverse to D. Okay, so one of them will be something like the D on P is a delta function, or delta form. Okay, and the one concept which wrote down. This was for M equals R3. And so, okay, so let's just write G equals R for simplicity. So this is just delta Xi D delta Xj, which D delta Xk over on ijk, right? This is the totally anti-symmetric tensor, and delta X, that's X2 minus X1. And there is a nice geometric meaning of this, is that what you do, you take a you construct a map from the configuration space of 2 points on R3 to just a sphere S2, and this is done by this map sending X2, X1 to delta X. And then you pull back the rotational invariant area form from S2 to the configuration space. Okay, and I will give a short example of how one calculates using with such a propagator. So we will try to calculate the first orders of the following expectation value. So this will be holonomy along L1. Oh, okay, sorry. So take L1 and L2, two links in R, or sorry, two-component link. So these are the two components of a two-component link. Of a link in R3. And then we take holonomy along L1 cross holonomy along L2. Right, so this is a, let's say, G cross G valued expectation value. So first, let's look just at the first order of the holonomy. All right, so holonomy, this is the path ordered exponential of the integral over Li of the connection one form. It is just 1 plus, the first term will be just 1 plus integral like this. Okay. So let's now plug this into the integral. 1 plus integral L1a, 1 plus integral L2a. So let's call this point something like x1. Let's call this point x2. So this is just there's one. So and now So we want to look at a term where there are two a's, because we need to connect two a's by the propagator. So let's look at such a term. So this will be an integral e to s ax1 ax2, and I swap the order of the integration. Okay. But so this term, according to the Feynman rules, what you should do, you should just do the first order of this Feynman expansion. You should just write the diagram. Okay, or in all orders, you should write diagrams which has these two as external legs. But here, let's just write a diagram like this, the first diagram, and to this one, the Feynman rules, they assign the propagator. So this as an element in G, and okay, sorry, no. Sorry, so the first order of amplitude will be just integral of L1 over L1 and integral over L2, where x1 is in L1 and x2 is in L2, and you just take the propagator. X1 and x2. Yeah. So here I took the whole algebra, so this will be G. This will be this quadratic element. And this is a not invariant, which is called the linking number. This is number of L1. Okay, so now I will go to a Chern-Simons theory of boundary conditions, and hopefully you can hop on. So if M has a boundary, so let's just take a very easy example, the upper half space. All right, and let's identify the boundary of M with the complex plane. So there is one. So if you just try to go through this, there is a trouble that this breaks. Like if you just try to look at all connections on such space-time, this breaks the BV formalism. Breaks the BV. So either you can also consider this failure of the BV formalism together with the BV formalism, and you get something that's called BV BFV. I don't think the F is for this failure, but yeah, it's Kratkin, I'm sorry. Or you can, so there's one possibility, and I think you will hear about it in Giovanni's talk, or like not in the context of Chern-Simons, but or the second possibility is to impose a boundary condition. And so this is what I will talk about in the second half of the talk. This is concerning these boundary conditions. So we will consider this so-called chiral boundary condition, which I think already due to Witten in the original paper. And then a generalization called V plus boundary condition, which is due to Chevera. And there is a general story about boundary conditions in this BV formalism, which we wrote about with with Friedrich and Pavel Schevera. So this is like subset. Okay. Okay, so let me tell you what the chiral boundary condition is. It's very simple. Again, for simplicity, let's start with G equal R. Then we just assume that that A on the boundary, which we identified with the complex plane, just belongs to. So this has a zero form part, one component part, and two component part, and we require that there is no zero form part. The one form part is holomorphic, and there is no restriction for the second. And I will come back to the V plus boundary condition later, but we would like to do this. We would like to do the same thing as before. We would like to find a propagator. But now, to be consistent with the theory, it needs to respect the boundary condition. So this D inverse needs to preserve the space of all such A's that satisfy the boundary condition. Okay, so, and this is our work with Pavel Schevera and Donald Humans. So this is the definition of the propagator, the propagator. And it's a nice picture, so I hope you enjoy it. Okay, so let us define a map. From the configuration space of 2 points on M on the upper half space to the configuration space of 2 points on the complex plane. I'm sorry, maybe I didn't say what the configuration space of 2 points is. So this is, by definition, this is M times M without the diagonal M, which is like without M, which is embedded diagonally. So we just take all pairs of points that are distinct. And yeah, or the ordered pairs of points which are distinct. Okay, so I will define this map. I don't know, let's call it R, and it looks as follows. So this is the bottom of the upper half space, and somewhere here you have 2 points which are floating. So now you find a big semicircle which passes through these 2 points and is perpendicular to the boundary. So let me draw it. There's only one such thing. This is also a hyperbolic geodesic passing through these 2 points. So this is a semicircle. So let's call these 2 points x1 and x2, and the 2 points on the bottom, let's call them z1 and z2, right? You can also, the one which is closer to x1 is called z1, the one which is closer to x2 is z2. So this gives you a map, right, from configuration space of 2 points on the upper half plane to the configuration space of 2 points on the boundary. Because yeah, x2. And then we just say that we just define a propagator, this will be just the pullback along this R of the following very natural form on this target space. So just dz1, which dz2 divided by z1 minus z2 squared. Maybe I should say that Yeah, okay. On if you see this as a form not on C but on CP1, this is a very natural SL2 invariant 2 form. Okay. So we hope that this propagator, it preserves the boundary condition. So this I can actually show that it will preserve the boundary conditions. Right, because if you check. Yeah. Because what was the condition is that if you set x1, sorry, if you right, let's take something that was made using this propagator as an integral kernel. So let's take integral of p x1 x2, I don't know, a x2 in M. And now we said that we want the result to satisfy the boundary condition. So we should look at the part where x1 is on the boundary. So we set x1 on the boundary. So but in this case, if x1 is on the boundary, then x1 is equal to z1, right? From this picture, it has to come from this x1 up, and then then x2 is not equal to z2, but x1 will be equal to z1. But then if you plug this in, you really just get dz1, because z1 is just x1, so dz1 is equal to dx1 in this case, and you get dx1 wedge something. Did I wait? No, I'm confused. No, okay, I'm sorry. I'm slightly confused, but the moral is that this dx1 coming from this term here will give you that the result satisfies the boundary condition. That's the boundary condition. Basically, because there's no dz bar. Okay, and so this is actually a good propagator, and we can try to do some calculations with it. But first, I will talk about boundary conditions, or the more general boundary conditions. So V plus boundary conditions. So for this, you need to write G as a vector space. You need to write it as a direct sum of two subspaces, such that the pairing is positive definite on the V plus and negative definite on the V minus. So this, you need to choose the decomposition like this. And then the more general boundary condition is that A restricted to the boundary should be in the following space. So there's again no zero form part. And so you say that the holomorphic part of the one form part lies in V plus, and the it should be 0, 1, sorry. The anti-holomorphic part lies in V plus, and the holomorphic part lies in V minus. And then there is no restriction on the on the two form part. Okay, but like there is no need to be afraid, because such P immediately gives you also a propagator which is compatible with this big boundary condition. Let's call it big P. If you just take P tensor, and here you take the, let's say, let me write it like this, EI plus tensor EI plus. So this is the inverse of of this pairing restricted to V plus. This is the inverse of the pairing restricted to V minus. The chiral boundary condition, this is just taking V minus is equal to G is equal to R. Okay, and so this is the propagator, and I will show you one application of the propagator, which we did in the paper, which is to calculate the RG flow of this theory. So the idea is that if you now try to write those Feynman diagrams that, according to the rules I explained above, some of them will diverge. So you do two things. First, you regularize. You introduce a cutoff. In this case, cutoff, which says that so if you have a propagator, you say that P is 0 if those 2 points on the boundary, those Z1 minus Z2, are closer than some value epsilon. And then you try to change the action functional in such a way you get, in the end, you get some kind of result which is independent of epsilon, such that epsilon going to 0 is independent of epsilon and well defined. Because yeah, as I said before, if you without the cutoff, if you send epsilon to 0, we are in a situation where some things diverge. Okay, and so the result in this case is that to one loop is that there's only one relevant diagram. And let me write it like this. So and here you put this P bar tensor E plus. And here you put P tensor E minus. So it only take like only take a part of the propagator on these two edges. And here, so this is kind of a technical thing. So these edges are not connected anywhere. So to actually to know what they are about, you put a G valued form on them. So alpha. And here we put another form beta. Okay, and then the integral you need to you assign to this to such diagram is the following integral. Right, so let's call this point y1. Let's call this point y2. They are both in M. So what you need to do, you need to take P, regularized with this epsilon of y1, y2, and P bar regularized with the epsilon of y1, y2, alpha y1, beta y2, and you also, so this is, let's say, the form part, and you also do the correct thing with the Lie algebra part. You need to contract alpha and these two parts of the propagator together.
Jan?
So yes?
Just to let you know, you still have 5 minutes.
I still have 5 minutes.
Mm-hmm.
Okay, that sounds good.
Mm-hmm.
Thank you. Okay. So if you try to do the calculation, which you can read in the paper, then you get that this I epsilon, it diverges logarithmically with epsilon. And what you get next to it is some kind of boundary term. And what you do, you take just the one form part of alpha, tensor the one form part of beta, and you pair it with the following, with something, let's call it TD. So TD is an element of V plus tensor V minus, and it is given by exactly by this diagram in Lie algebras. So okay, so this was the cutoff part of the renormalization, and now, so there is like one needs to look if there are some nice counter terms which can change this logarithm, which can remove this logarithmic divergence, and they are, and what you need to do, you need to change V plus to depend on epsilon. Okay, again in some logarithmic, like in some way which diverges logarithmically, where this as epsilon goes to 0, and this is written in the following way: 1 plus d log epsilon bar, and here I put this TD acting on V plus. So what do I mean by this? So remember that this is Lie algebra G, and it decomposes V plus and V minus. But then if you have a map from V plus to V minus, so TD is now seen as a map from V plus to V minus using the pairing, right? Because you can, this is isomorphic to V plus dual. So since TD, if you see there's a map and you look at the graph of this map, like something like this. So this is, so a map from V plus to V minus, this is the same as a deformation of V plus. Okay. So this is the correct prescription. And let me finish with a motivation more maybe for this story. And these are the 2D sigma models. I will be very brief. And is that by work of Chevera, if you take a Chern-Simons theory with this V plus boundary condition, and another condition I will not talk about, these are equivalent as, let's say, Hamiltonian systems with 2D sigma models. And then it's like there's a question whether they are equivalent more than just some kind of classical models, whether they are equivalent quantum mechanically. And the renormalization group flow for these sigma models, it was known, RG flow. Of this kind was known, and it was given exactly by this diagram. But I think I think Friedrich is an expert on this, that the calculation to get this is horrible. There are a lot of diagrams, it is not easy. Unlike here, where it comes from just one diagram. Okay, and the last sentence I say is that hopefully you can also find if you are in a situation where you have a Chern-Simons with boundary, and then you could maybe try to look if your boundary condition can be cast as this kind of V plus boundary condition, which is pretty general. And then you have a propagator, which is very geometric and nice, and you can try to do some, I don't know, loopy calculations with it. And with this, I will end. Thank you very much.
So thank you very much, Ján, for this very nice talk. Yes, questions. Okay, we have one question from Nima. Nima, please go ahead.
Okay. Yeah. So it seems that the story might also be related to the Quran Sigma model in a sense, right? So yeah, can you maybe say a couple of words on that?
I didn't have time to go into that, but in the same way you can define the Chern-Simons theory, you can define a Quran Sigma model. This is again an AKSE construction, and the propagator works. There is some there you need to do a little bit. In addition, you need to add also some kind of Kontsevich-like propagator. But then you have and then you get a slightly more general picture than just this one. But the theory, it goes through, and you can talk about the normalization of those Quran Sigma models. But I have to say that this is slightly more mysterious because there's this dependence on the base, and there are lots of diagrams which come from that. So I have to say I don't understand it completely. But the story goes through also for Quran Sigma models.
So another question was, so you split it your algebra, right, into two spaces. So do you want to have a Manning triple, or is it?
No, necessarily. No, they can be like, I guess as you saw, like the chiral boundary condition is the case where one of them is the whole thing and the other one is nothing.
Okay.
They're like, or like Manning triple. These two V plus V minus, they are not Lagrangian. They are they are close with respect to perp.
Okay, thank you.
Okay, then we have another question. Andre, please.
Hey, Jan. I have a question about those propagators at the beginning. So the usual physicsy way I would do that is that if I have gauge theory, it has a singular kinetic term, right? So I need to gauge fix, and for gauge fixing, I need the metric, right? At least for Lorentz gauge fixing, for instance. And so how come there's no metric? And there was the famous thing in Witten's paper, right? When he actually showed that when you gauge fix, there's actual dependence on the metric, but then it doesn't really bother us that much. But how come it doesn't really enter at all in that Kontsevich mysterious propagator, like no metric like dependence or extra structure of any kind?
Yeah, I think like the answer is that like since this is R3, you just have a canonical metric there, and that's the one he uses, I would guess.
Okay, so there's I see. So, do you know which gauge fixing is it in? Like is there?
I think this is the Lorentz gauge. Maybe Konstantin can confirm, but I'm not sure.
Yes, indeed. For the Kontsevich propagator, it should be Lorentz gauge.
But also for the Axel Rotzinger, no?
Yes, absolutely.
So how are they different then, if they both come from same gauge fixing? It's just inverted kinetic term. They should be same, no?
I guess that I'm not sure, but I guess that like I'm not sure, but okay. I think that if you ran the Axel Rotzinger procedure with these very specific choices, you would actually recover Kontsevich's propagator. But this I didn't do it. I don't know.
I see. So is it so and the Kontsevich formula, that's just for R3 with canonical metric. That's what you're saying then.
But you can also like especially if you study these kind of this normalization phenomena, this is basically all you need, because like locally everything looks like that.
Right.
Or okay.
All right. Okay. I see. Thank you. Thank you.
Okay, maybe we have time for one last question. So, Eugene, please go ahead.
Yeah, hi. Thanks for the talk, Jan. I just wanted to ask if these propagators with boundary condition, if they're related to propagators you might obtain by like sort of what I think it's called mirror image method.
I don't think so. No, I don't think so. So there are also mirror like for different boundary conditions, those mirror images would work, but this is not that.
Well, you could try to mirror image. How do I put it? Like you're still asking for some components to vanish, right? So you could still sort of mirror image those components, if you see what I'm saying.
So like let's say mirror image and complex conjugate or something.
Yeah. So for example, yeah, something like that.
I can tell you that when we were looking for the propagator, like I was trying something like this and I didn't get anywhere with these mirror rings.
Okay. Yeah, sorry, because that's sort of how I have a method, or not method, but that's generally the way I would obtain propagators, is by mirror reflection, but maybe it doesn't apply in this case. I think it does apply for the chiral boundary condition, but I don't know about the V+ ones.
Okay. That's interesting.
Maybe I can ask you about it later.
Thank you.
Okay, so if there is not any other question, let's thanks the speaker again. So thank you, Ján. And I would say that we restart at 5 p.m. so we can take a 5-minute late/early coffee break. And yeah, we'll meet here at 5 p.m.